Here's a quick review on how to graph rational functions. In this case, I entered this into Desmos, so we already have the graph partially done. But this is how you would start it. Step one, you always have to factor. So we're going to factor the bottom because that's where you will find the restrictions on x. And the two things that multiply to give us 30 and subtract to give us 1 are going to be 5 and 6. And I want the 6 to be positive and the 5 to be negative. So the restrictions on x are x cannot equal negative 6 and x cannot equal 5, because if they do equal either of those things, you would have a 0 in the denominator, and we cannot divide by 0. So that's the first step. They may be asymptotes or they may just be wholes. Next step after you factor is to factor the numerator, okay? So let's factor the numerator, and I multiplied my 2 and my negative 5 to get negative 10, and my two missing numbers that will multiply to give me 10 and be opposite signs to give me negative 9 are 10 and 1. I want it to be a negative 9, so I'm going to do a negative 10. And in the interest of time, I'm going to just factor this the way that I would do it, which means I know that the first terms have to be 2x and x, because that's the only way to make 2x squared. I also know that I want to make a negative 10 and a 1 with these outer and inner, and the only way to get 5 is to use 5 and 1. So I'm going to put a 5 here, I'm going to put 1 here, and lo and behold, 2x times 5 is 10x. 1 times x is x. I want it to be a negative 10, so I'm going to make this guy negative and this guy positive. So now I have my fully factored expression. It's got a 2x plus 1 times x minus 5 on the top, x minus 5 times x plus 6 on the bottom. All right, let's fill in all of these forms. The restrictions on x are from the denominator, and x can't be negative 6 or 5. But if you look at this problem, you can see that we're going to be able to cancel out the x minus 5s, which means 5 is a removable discontinuity. If it cancels out, it belongs in the wholes section. But the one that we can't remove is negative 6. That's going to be our full-on asymptote. Now, the zeros come from the numerator. So our new function, let's just rewrite this new function so that it's usable. We're going to write y equals, what's left is 2x plus 1, that's left on the top, and what's left on the bottom is x plus 6. So next up, we would need to find the horizontal asymptotes. So if you want to copy this down, hit pause, and we're going to continue this after we find the horizontal asymptotes. So here's how you determine what the horizontal asymptote is. If it's not in the easily translatable form that we were used to, when it's like this, we have a few options. We have to look at the highest degree. So in our case, our numerator is a second degree, it's an x squared, and the denominator is also a second degree, it's an x squared. And so if you look, we have situation 1, where the degree of the numerator and the degree of the denominator are the same. So I'm going to write the 2x squared. I'm just going to put the leading coefficient, and I'm going to put the leading term. And we're going to just care about the coefficients of both. So that has a 1. So what you do when the numerator and the degree of the denominator are equal, you look at the coefficients, and you just say the horizontal asymptote is equal to 2 over 1, which is the same as saying 2. I have an additional example over here, and you could look at that. We're saying if you had an x squared and an x squared in the denominator, just like here, but the coefficients are reversed, the horizontal asymptote is just the coefficient of the top over the coefficient of the bottom. So they were 1/2. We're going to be having situation 1, but I think we should just take a quick peek at the other two situations. When the degree of the numerator is smaller than the denominator. For example, we were learning about inverse relationships like 1 over x. Well, the top is an x to the 0, and the bottom is a first degree, it's an x. So the degree of the numerator is smaller. That horizontal asymptote is 0. Same thing, you might have like x plus 6 over an x squared. Again, this is a first degree, x to the 1. This is a second degree, x to the 2. Whenever the numerator is a lesser degree, the horizontal asymptote is just defaults to being 0. So finally, our third one is, we're going to encounter that a few times, and what happens there is if the degree of the numerator is larger, for example, you have an x to the 5th and you have an x cubed, when the degree in the numerator is larger, we have a 5th degree and a 3rd degree, there is no horizontal asymptote. And we'll have a few situations like that that we'll explore. But we want to get back to our situation, which is situation 1. So remember, we just took the leading terms in both of our numerator and denominator, and we ended up with a 2 over 1. So we said that the horizontal asymptote is at 2. So let's get those both graphed. We're going to put in a vertical and a horizontal asymptote. So here at -6, we're going to put in a vertical asymptote. You can use a solid line, you can use a dashed line, whatever you feel. And the horizontal asymptote is at 2. And you can kind of see that it looks like these are in the right places. So now we have one more thing to do. We need to find what are the zeros and what does this 5, this whole, mean. So take a second, and to get the zeros, it's where the numerator is equal to 0. So we're going to add that to our list of things. So we're going to say the third step is zeros. You're going to set the numerator equal to 0. So we're going to say, okay, well, 2x plus 1 equals 0. What does it take to make that happen? Well, we're going to get 2x equals -1, and we're going to end up with x equals -1/2. So it means that at -1/2, there should be a 0. We should cross the x-axis at -1/2. And if we go and look, we can see that that actually is happening right here on the graph. So we would add that in as a possible point. I graphed it for you, so you didn't have to do that. But this is a way to get an additional point pretty easily. So our last step is going to be, what do we do with these wholes? So what does the whole mean? Well, if you graphed this in Desmos, and not 2x plus 1 over x plus 6, but the actual original function, if you traced it to where x is 5, the point that would come up would say 5 and undefined, meaning that there is a hole at that point. The graph doesn't exist there. So what we're going to want to do is at 5, we're going to put a hole, all right? So we're going to kind of draw it like this with a big kind of open circle there. And you would stop the graph there and continue it on the other side. It wasn't an asymptote because we were able to cancel it out. We were able to kind of like patch up the wall there. But there's still a little spot where the graph doesn't exist. So what we're going to do is we're going to find out exactly where. Now, if we look at our graph, it looks like it's at 5, 1. But remember, you wouldn't have the graph already presented in front of you. You would have to find out where this point is. So we're going to take our hole of 5, and we're going to say, okay, when x is 5, where is y? In our new fancy function, where 5 is legal. So let's put that in. We're going to say, okay, when x is 5, we're going to get 2 times 5 plus 1 over 5 plus 6. So when we do that, we're going to get 10 plus 1 is 11, and 5 plus 6 is 11, and an 11 over 11 is 1. So when x is 5, y is 1. So what that says, it doesn't mean that y actually equals 1. What that means is at 5, 1, there's a discontinuity. The graph doesn't exist. There's a hole in it. There is a hole. And that's what you would need to do. You'd get your horizontal, you'd factor, get the restrictions on x, see if any of them are removable, get them in their correct spots. Things that you can remove are holes. Things that can't remove are walls. They're asymptotes. Get your horizontal asymptote, mark them in the picture, and then you are going to find any zeros, put them on your graph. You are going to figure out where the hole is. And the way that you would get the other points on the graph would be to go to the left and right of each asymptote. You would just pick a couple of points to plug in just to get an idea of the shape of your graph.